So last time we brought up the kinetic energy due to rotation right here, and we said that all of our letters just get switched to rotational letters, and our M got switched to I, where I is called our rotational mass. It's how hard it is to spin something, resistance to spinning. And we said that was the sum of M sub I, R sub I squared, where R is how far out you are from the axle. And we said for a disk, you get 1/2 M times the outer radius squared. For a hoop, it was MR squared. And for a sphere, it's 2/5 MR squared. And we said for any round object, we could just call it squiggly MR squared, where squiggly is a 1/2 for a disk, 1 for a hoop, 2/5 for a sphere. So now, let's just say we're going back. We've done this problem enough times, but all the times that we've done it before, our pulleys were massless and frictionless. Now we're just going to make them frictionless. Well, when I say frictionless, I mean no friction on the axle. There has got to be friction here. I don't want the rope to slide over the end right here. The rope, matter of fact, the speed of the rope, as the rope goes this way, it's going to be the same as the speed of the rim on that pulley. Why? Because I don't want the rope to slip on it right there. So let's say we're given a problem like this, no friction here on this surface. And let's just say we release it from rest and we ask, what is the speed when it gets to here? Now, what we would have done before is with energy, we would have said all the energy was just, he had hogged all the energy, because I'll call H equals 0 here, up there at this point. So here was my H equals 0 for that block. Here's my H equals 0 for this block. And since there was no kinetic, we would have said the energy to begin with was all the M2GH. M2GH. Now, when he dropped, he lost it all. Where did it go? It went into moving this guy. This guy now has a speed, 1/2 M2V squared. This one would have the same speed because they're tied together. So you got plus 1/2 M1V squared. But we are now, this is what we would have had before, but now we also have energy due to this guy spinning right here. And he's spinning with this much right here. He's got 1/2 times his I, but it's all of our pulleys are discs, so it's another 1/2 MR squared. Times the omega squared right here, omega squared. But there's a relationship. Since the rope doesn't slip on this surface, the velocity of the rim is the same as the velocity of the rope. So it doesn't slip on there. Well, the velocity of the rim is R omega, and the velocity of the rope is just the same as the velocity of the blocks, that's V. So I can turn my omega into V over R. And that's what we'll be able to do, because none of our ropes are ever going to slip on the pulley. So we can say the rotational rate of the pulley is the speed of the rope going over it divided by R. So if I take and come down to here and plug in for omega, that's V squared over R squared when I square them right here. So this right here will be V squared over R squared. You notice the R's cancel out. And so all I get is 1/2, and this would be the mass of the pulley. Mass of the pulley. And so we have V squared, and V squared. They're all the same V. So we'll factor that out, V squared. We can factor out, they all have a 1/2 in them, so we'll pull out the 1/2. And we're just left with, let me put that term first, M1 plus M2. M1 plus M2 plus 1/2 mass of the pulley. Plus 1/2 mass of the pulley. Okay, and that equals M2GH. So, if we wanted to solve for the velocity, we'll bring the 2 up to here, take all this mass down below, and take the square root right here. So we can work out ones with pulleys on them right now. We don't want to look at forces, that'll be the next chapter, but at least we can use energy to find the velocity. Okay. Well, what happens if we're rolling right here? You know, here we have an object, and it's just rolling along the ground right here. Which kinetic does it have? Does it have this kinetic, or does it have this kinetic, or does it have both? Here I have this thing rolling right there. It's rolling, or I can just have it roll down this thing right here. It actually has two. This motion is made up into two motions. Rolling right here, is equal to this motion plus this motion. So this, anytime you're rolling, you have both kinetics. So right here, you're going to have your total kinetic. You have 1/2 mv squared plus 1/2 I omega squared. You got both when you're rolling right here. And when we're rolling, I don't think we have any cases where you're actually slipping right here. What does that mean? That means that every time this goes around one time, this object moves the circumference right here. So if we say rolling and not slipping, which is all of our cases will be rolling and not slipping, we can say that the speed of the center right there is the same as the speed going around here. Why? Because every time this thing goes one circumference, that's going to move one circumference right there. So we can say the speed of the rim is the same as the speed of the object right here moving, which we call just v. There's v right there. And the speed of the rim is r omega. So we can say that omega and v are related right here. So we can turn our omegas into v's. So we can say omega equals v over r, plug it up into here. So when we're rolling, the total energy, total kinetic, is 1/2 mv squared plus 1/2 I times omega squared, which is v squared over r squared. V squared over r squared. So there's the total energy you have when you're rolling right here. Okay, now I could also ask how much, even though you're moving, what's the work due to friction? There is friction here. If you didn't have friction, it would slide. But remember, what's our definition of work due to friction? Work due to friction is equal to minus the friction times the distance you slid. When we're rolling, we're not slipping. So the work due to friction is always going to be 0 right here because you're not slipping. The S is 0. You're not slipping. The S is 0. The friction is non-zero right there because you do have friction. You notice if this thing were slipping like that, you know, there has to be friction right there. Otherwise, it would just slide along right here. At least to get it going, there had to be friction. Okay, so now what I want to do is I want to show a demo of, suppose we were to put an object on an inclined plane, a round object, and race different round objects down. We said I for a round object with squiggly mr squared, where squiggly is a half for a disk and it's a 1 for a hoop and so on right there. So this is for any round object. Okay, now we're going to start it from rest, let it go, let it come all the way down. When it gets to the bottom, it's rolling, so it's got both kinetics. So when it first started out, it had potential energy. If this is H, it started out from rest. There's the energy at the top. When it got down to the bottom, it had both of them right here. So it had this one, which is 1/2 mv squared plus 1/2 I, which we said was that, squiggly mr squared, v squared over r squared. V squared over r squared. Now you'll notice by looking at this, there's an m in every term, they're gone. These r's drop out too, right here. A lot of stuff drops out. You notice there is friction here, friction, if you let this thing go, this thing's trying to turn that way. There's a friction actually in that direction, but it's not slipping, so the work due to friction is 0. Okay, so what do we have? We end up with GH is equal to, let's multiply by 2, so that way we don't have these two. And we can pull out the V squared out of these two terms. We're left with 1 plus squiggly. Or take this down below and take the square root. So the velocity at the bottom is the square root of 2GH all over 1 plus squiggly. So we can see from right here that the larger the squiggly is, the smaller the velocity is right here. So, and I assume whoever has the largest velocity down here will win the race right here. So if we looked at something like a hoop, that was squiggly was 1. The velocity, this would just be 2. The 2's would drop out, it'd just be the square root of GH. Velocity would be the square root of GH. If we did it for the disk, squiggly was 1/2. 1/2 plus 1 is 3/2. The 2 would come up, that's 4/3. So this is V equals the square root of 4/3 GH. You notice this is bigger than that. So the disk should beat the hoop right here. And we might as well, since we have the sphere in there, the sphere, squiggly was equal to 2/5 right there. And you notice the mass doesn't matter on this thing, so it didn't matter who was the heaviest right here. The mass has nothing to do with it. The radius has nothing to do with it. The only thing that matters is if they all start from the same height is the squiggly right there. Well, if you put in 2/5 right here, 1 plus 2/5 is 7/5. 7/5, that's 10/7. So that's V equals the square root of 10/7 GH. Well, let's just race these down. Now, by looking at this thing, this one looks like it's going to be the last one. This one is by far the smallest because this is bigger than 1 and that's bigger than 1 right here. So if we were to measure, say, the hoop versus the disc right here, right there, you see, notice the disc is just going to, and I could switch places right there. Disc is going to beat out the hoop. The hoop, does that mean the hoop's always going to be the last? No, there's one that always loses to the hoop, and that's the square. Square never makes it down first. Right? For any round object, the hoop is always going to lose. Right? So, well, let's look at between, say, the sphere and the hoop. Again, the radius doesn't matter, because you notice there's no R down there. The mass doesn't matter. The only thing that matters is the squiggly. This squiggly is 1, this squiggly is 2/5 right here. So if we put these down there, you notice the sphere, the smaller the squiggly, the less energy it takes to turn it right here. And so all that potential energy here, a lot more of it gets to go into moving it right there. Now if we compare these two right here, now we're comparing a half, well, that's 5/10 with 4/10. It's not much different. This one's slightly smaller. This is 4/10, this is 5/10. So it's going to be a close race. We might have to do it by the sound right here, but you notice that one's a little bit in front. Let me put it right here. You notice it's out just a little bit in front right there. It's not much right here. Now, suppose I got this from the geology department too. Looks like some sort of core sample from a rock right here. Which one's going to win between these two right here? Well, aren't they both this right here? It's just that this has a small radius and it's a fat disc. This one has a bigger radius and it's skinny. They should take about this. They should take the same amount of time to get down right here. So I'm not quite sure how to race them right here. Right there. You notice it's exactly. Oh, actually, I should start it right here. Right there, exactly the same amount of time. again, they both have the same squiggly right here. Here, I have a handball and this ball right here. Which one is going to win between these two right here? Well, the difference between this is this one is a solid. I can see right through it. There's a hole drilled, but it's solid. This one I know is hollow. Which one's going to beat between the hollow and the solid? Well, if you looked at these two, which one won? It was the solid. Solid always beats the hollow right here. So I'm assuming that this one will win just because it's the solid right here. Better over here so you can see it. You notice it's out in front right there. I'll try it again right there. So we can see that he just wants to go sideways. That's my only problem right there. But we can see that the solid always beats the hollow. Suppose I didn't know that, let's say no one drilled a hole in it, I couldn't look inside of it. How could I tell whether this was solid or not without destroying it? Well, what I could do is, I could find, let's say, a pool ball. I know pool balls are solid, and I race this against a solid pool ball. If they both take the same amount of time to get down, this would be solid. This thing could never beat that, and if it was behind it, then this thing has a cavity in it. And the more it was behind, the bigger the cavity would be. So you have a non-destructive way of testing whether something has a hole in it, a sphere has a cavity inside it or not. This is also a way you can test whether an egg is hard-boiled or not. You can go like this with a hard-boiled egg, but try doing that to a raw egg. You just can't spin a raw egg. Try spinning a raw egg. It just won't work. And even if you do finally get it going and you stopped it momentarily and took your hand off, you notice this stays stopped. If it was a raw egg, it would start spinning again because the fluid in there is still moving right here. Here I have another disc right here that we can race against this disc right here. And so if we race these two against each other, this one right here only goes uphill. It's one of those upward hill ones right there. So sometimes they can go uphill, but so I can't really test that one right there. But now, suppose we went to the supermarket and decided to roll down different cans. Maybe you want to roll down Coke and Pepsi to find out which is the best right here. Or maybe Coke versus Diet Coke, see which one gets down faster right here. Well, I did that. I went to the grocery store, the long board, rolled down a bunch of different cans, and I plotted it out. So on this axis is the size of the can, and on this axis was how much time it took to roll down, all starting from the same spot right here. Now you'll notice tomato paste, little itty bitty can. I guess you don't need much right there. The dog food, the kind where you got to dig out with a fork right there, and the refried beans, huge can right here. You raced them all down. They all took the same amount of time to get down. Why? Because they're all solid cylinders right there. But if we look at a can of Pepsi right there, here's Pepsi down there. Pepsi, and that wasn't even Diet Pepsi right there. Pepsi got down real fast. Why did Pepsi get down so fast? Well, if you look at, say this is the can of Pepsi. You got Pepsi in there. And now you let it go and you watch. If you could see the Pepsi in there, the Pepsi would not be spinning around because the can is so smooth on the inside. The Pepsi is just going like this. The only thing that's spinning is the can. So all that Pepsi helped you with potential energy, because there's Pepsi weighs a lot, but the only thing that's spinning is the can. The can weighs almost nothing. So almost all the energy gets to go into this term, and that's why it's going so fast at the bottom, and that's why it gets down so fast. So suppose you had 3 cans of Pepsi. You have one that's frozen, one that's liquid, and one that's empty. Which would get down first? Well, according to this, the Pepsi, the one with the liquid in there, would get down first. Remember, the solid would be like this, up where the tomato paste and the dog food was. That would be if it was solid, and if it was empty, empty would get down last right here, because remember, this one always loses to this one right here. So, now, if we look at the other aisle, the soup aisle is all these different cans. They all the same size, but they have different stuff inside of them. And this one up here took the longest of the ones I tried. Chicken noodle soup took forever to get down. Why did chicken noodle soup take so much time? Well, what's in chicken noodle soup? Certainly no chicken. Maybe some noodles and chicken flavored water is all it is right here. So here, if we look at this, now we have a can of chicken noodle soup. The noodles are hanging out here at the bottom. As this thing rolls, they're sliding along the bottom. Now you got some work lost due to friction right here. Well, what's that going to do? That's going to slow you down right here. And what does that go into? It goes into heat right here. So if you're up camping and you can't make a campfire, what can you do to heat up your soup? Just start rolling it down the mountain. Keep running down the mountain. Maybe by the time you get to the bottom of the mountain, it'll be a little warm enough for you could open it up and eat it right here. But it's going to take a lot of running to catch up. And now as we keep coming down this way, you'll notice the soups, this is cream of chicken soup. That's definitely thicker than cream chicken noodle soup. So the soups get thicker and thicker as you come down this way, right here. Now I've seen a commercial that says they have the thickest chili. How could you determine whether they really have the thickest chili without even opening up the can? Well, all you have to do is rice them down. Whoever gets closest to this line has the thickest chili. Now, the only thing is I don't understand, who wants chili this thick? That's pretty tough eating right there, but that's what, if you really wanted to be down on that line, that's thick chili right there. Now, suppose you did this for every single can in the supermarket. Put it on a big plot in your kitchen right there. And now you're really hungry and there's a can of food in the pantry and the label came off and you say, boy, I wish I knew what was in here and I'd like to know before I open it up. How could you determine it? Well, you roll it down your inclined plane, look at your calibrated scale, and then you can say, it's either beef stew or dog food. Well, then you run into a little bit of a problem because even after you open it up, you still can't tell the difference. So it might depend on how hungry you are right here. So if you see anyone taking a big board into supermarket, they're probably just trying to find out which is the best right here. I guess if you get down first, you're the best right here. So again, the only thing that really mattered was the shape of the object, which is really this squiggly right there. Okay, so give you something to do while you're at home. Stuck at home, just roll some cans down an inclined plane problem. Go into the pantry and roll them down. Okay.